Solving an equation with rational exponents is very similar to solving an equation with a radical. The similarity is that we need to do inverse operations in order to isolate the rational exponent. We need to get the equation to the point that the rational exponent is by itself. Once the rational exponent is by itself, then we can use an inverse operation on the rational exponent to simplify. In this example, the rational exponent is already by itself on the left-hand side. This 1/5 power right here is the exponent of the entire expression 5x plus 3, thanks to the parentheses. In order to undo or invert the operation of the 1/5 power, we're going to raise to the power of 5. Remember, we have our rules that says when you go power to a power, you multiply. So if I multiply 1/5 by 5, that just leaves me with a power of 1, which is just the regular old expression 5x plus 3. We're going to do the same thing to the right-hand side, where we raise -2 to the 5th power. That's an odd base raised to a negative base raised to an odd exponent. In that case, our value is negative. You'll see that the radical expression, if you want to think of 1/5 as the 5th root, the radical expression, or the rational exponent is gone. We're down to a regular linear equation that we've solved countless number of times, and we get x is equal to -7. Just like with any rational equation, any radical equation, these rational equations, we want to check our solution for potential extraneous. So we're going to check x is equal to -7. Inside of the exponent in the original question, we have 5 times -7 plus 3. 5 times -7 is -35, plus 3 is -32. Then -32 was raised to the 1/5 power. You ask yourself the question, can I raise a negative base to an odd power or an odd root? And in this case, an odd root, in this case you can. The 1/5 power of -32 is just -2, which is the original equation that we had. So this answer is good. Rational exponents treated just like our radical equations, we try to isolate. Here we'll have to do a little bit of work in order to get the rational exponent to the point that it's isolated. We'll add 1 to both sides of the equation, and we get 4x to the 3/5 is equal to 32. We divide both sides by 4, giving us x to the 3/5 is equal to 8. Now this power is going to be a little bit trickier. In the last one, we were able to just multiply by 5 because it was just a 5th root. It was a 1/5 power. We want to choose our power so that this exponent ends up being a 1 when it's all said and done. You can do it in 2 separate steps. You can do a raise it to the power of 5 to get rid of the root, and then raise it to the power of 1/3 to get rid of the exponent, or the numerator of the rational exponent. I'm not going to do that. We're going to take the whole thing out in one move, and we're going to do that by raising the entire left-hand side to the power of 5/3. Again, we're going to multiply these exponents together because it's power to a power. So we end up with just x, and 8 is going to get raised to the power of 5/3. Remember what the power of 5/3 means. This is the root, and this is the exponent. And you can do them in whichever order you want. Could you do 8 to the 5th and then try to take the 3rd root of that? Sure. But it's probably going to be a lot easier to take the root first, then raise it to the exponent. So the 3rd root of 8 is 2, and 2 to the 5th power is 32. So we get, excuse the technical difficulties, we get x is equal to 32 as our final value. And if you need to check on that one more time, it would just be the 3rd root of 8, which is 2, and then 2 to the 5th power, which is 32. We check our answer. 4 times 32 to the 3/5 power minus 1. 4 times the 5th root of 32 is 2. 2 to the third power is 8 minus 1, and that gives us our 31. So our answer checks out. Our solution, x is equal to 32. In our last example, we have the rational exponent already isolated. So it makes sense that we can jump right to raising to the 7/2 power. While that eliminates the power that is on the left and leaves us with just x plus 4, we need to do the same thing to the base of -4. Raising the base of -4 to the 7/2 power, just like we talked about, you could either take the power first and do -4 to the 7th power, or you could take the square root of 2, or square root of -4, excuse me. That is the decidedly easier route, and actually it's the decidedly better route, because as soon as you try to take the square root, you realize that this base is negative and this cannot happen. So we stop and we suggest there's no solution. Trying to raise a negative base to that square root power is not going to work. You cannot take the square root of a negative number. So we make sure that we check this against the number that's here before we try to go through all of the work. In the event that you did do this first and you were able to create a positive number that you're going to take the root of, chances are that the extraneous solution would catch that mistake. But we don't even have to go beyond this point because we see that we cannot take the square root of -4, so we stop. So thinking through these last 3 examples and the similarities in there, we're looking to isolate our rational exponent. We're looking to do inverse operations in order to do that, and we're thinking through what it means to raise to a rational exponent power. And we're catching those situations, hopefully, where we aren't actually able to perform the operation. If you catch that situation before you go through all of the busy work, then you can stop and say there's no solution.